So we are going to talk about, no, 1, 2, 3, good. Yeah, this talk is about garbage collection, but garbage collection at the different levels. All of us know that we know like garbage collection for ages, right? Because we know like different types of GCs, we create Java applications, we know how to tune, we know how to do performance analysis, we know how to find bottlenecks, etc. But in fact, garbage collection is not unique to Java. It also happens at the database level and even hardware level. And why would you care about this? First thing first, that's an opportunity for you to learn something new, something that happens beyond the Java ecosystem, and how other best-in-class technologies use garbage collection. Because when I started coding in Java, I still remember the time when some people like who were using C++, etc., they would come and say, hey, Denis, like, come on, it's like JVM, you have garbage collection, it's always slow. But then when I learned that some of the well-known databases and even hardware uses garbage collection, right now I can throw these people some argument in their faces saying that, hey, check PostgreSQL or check SSDs. Those technologies also use garbage collection. And also, like, if you know that details, whenever you come across any performance bottleneck with your application and you use a profiler, you use some other tools, and you don't see any symptoms at the application level or JVM level, then you will know where to look at. Because sometimes garbage collection also can impact performance of your application, garbage collection, let's say the database level or SSD level. A little bit about myself. My name is Denis. I have been working with distributed databases and systems for the last 8+ years. Presently, I'm with Yugabyte that develops YugabyteDB. That's a distributed SQL database built on Postgres. Before this database, I contributed daily to Apache Ignite. That's another distributed database, but for high performance and memory computing. And prior to this databases journey, I used to work at Oracle and Sun Microsystems developing JVM and JDK. So that's why, even though I'm still a database guy, I want to stay connected with the Java community and show something new to the Java developers and architects. And by the way, today, welcome a friend of mine, virtual one, Java Joe. He didn't manage to come here, but he is going to tell his story. Java Joe is a principal architect and engineer. And imagine that right now he's developing a service for a new pizza chain company. Pizza again. Not the best joke today. And Java Joe considers the following architecture, the simple one. He's going to use Spring Boot, web services. And initially, the architecture will be using PostgreSQL database. Who uses PostgreSQL? Anybody? And the data is going to be stored on SSDs because it makes sense, not hard drives. But also, the goal is to create a service for a pizza chain. The first version of this, the first pizza shop will be opened in one store. That's why the scalability of PostgreSQL will be enough. But once this pizza chain goes nationwide, he needs to scale. He needs to scale the application level. He needs to scale the database level. And this is why he considers YugabyteDB. This is why when he came up with this architecture, he wanted to check and test both technologies to see what happens when he runs his application on top of these databases and on top of those SSDs. As a disclaimer, this talk is not about, let's say, what is better, PostgreSQL or YugabyteDB. Both databases complement each other, but you will be able to see, because both databases, they use different structures, how they store the data, and they use different types of garbage collection techniques. So that will help you to see, just learn even much more from that perspective. And what Joe did, once he created the first version of the service, he did the load test, a simple load test. He loaded 1 million records through the Spring Boot REST endpoint into PostgreSQL database. Then he executed a few million updates and deletes over this database. And eventually, when he checked the database size, after deleting all of the data, for some reason, the database size initially exceeded the initial size of all of those 1 million records. And he got confused. What's happening? I inserted those values, I updated those values, and then I deleted those values. Why the data is still in the database? And the size of the total size of this data exceeds the initial size of those 1 million records. So right now, let's walk through the summary of Java JAWS investigation, because he's a principal architect, and he always is looking for answers for different situations, such as this one. When he started looking at Postgres, because Postgres was the first database, he again reminded himself about multi-version concurrency control. So what this is for? Like database, if you let's say run PostgreSQL on one server machine, usually this database has to process like hundreds or thousands of operations like every minute. And it's a highly concurrent system. And somehow when you run two transactions, the transactions might be updating the same rows, they might be updating the same columns of the same row, and the database has to ensure that all of the updates are consistent. The database cannot allow itself to corrupt your data, right, or to overwrite one data with another. And this is what multi-concurrency control is for. Let's take this example. Let's say that you have transaction number 1, and this transaction has just started. You have this begin statement. And right now, the value of the status column for a pizza order is set to ordered. And then another transaction comes in the database, and this transaction updates the status of this order to baking. The pizza is being baked. After that, the first transaction wants to select the status of this order and what should be returned by the database. The database has to return this value because the second transaction started later than the first one, and this value is not committed yet. It will be committed sometime in the future. And this is what happens with the multi-version concurrency control. One of the transactions might see the older values for different columns, for different rows, and the database, such as PostgreSQL, it has to keep multiple versions of the same record. So let's take a look at this. Let's do this experiment. So Java Joe prepared a few slides with his summary, but we will skip them through because instead I want to show you the code and how it works in practice. So what we have prepared so far. Who uses Spring Boot? Okay, like nobody needs an introduction. So what I have here, folks, let me show you around. Okay, this one we will hide for now. So we have a one entity class pizza order that corresponds. It has 3 columns: order ID, status, and we have the order time when the order was put into the queue. Also, we have a simple repository like this one, just an extension of the GPA repository. And orders controller. Here we have a few REST endpoints. We can put a new order in. We can change the status, and we can change the time, and we can also delete an order. Nothing new, right? But now let's do this. Let's connect to our database. I'm going to use PostgreSQL. It should be empty. Yep, we don't have any relations, no any tables yet. Now let's go to the app and start this application. When the application starts, it will create the schema on the fly. So right now, if I go back to Postgres, you'll see the pizza table is created. And if you do this, you see the structure, the order ID, the status, and order time. All of those columns are mapped to the fields of our entity class. So what's next? So right now the table is empty, right? And also we are going to use some special function, and that function allows us to look into the memory of Postgres. You can see how many versions of a given record we have in the database. So the function name is from Heap page. So Heap, like Postgres has the notion of the heap, but don't confuse it with the Java heap. Basically, a heap in Postgres is a synonym for a table in Postgres. It accepts the following parameters: the name of my relation, pizza order, and the range of the pages. I want to see all of the records in the first page, from 0 to 0. And right now, there is nothing in Postgres, no any records. Let's change this. So I have this REST endpoint. Yeah, so let me see. This one posts, adds a new order into the system. Let's execute it. And if we go back to my Java application, you can see that the request went through the Spring Data JPA, and Hibernate generated this query for us. The data is inserted in the database. So let's run this select. We have this, let's do it this way. We have this record, but also let's look into the memory. Okay, this is my record. The state says that that's just the normal, meaning that this record is alive and it's visible, and that's what's going to be returned whenever you execute this select statement. This one, xmin_age, it's like it means that the number, the ID of the transaction that added this record into the database. Xmax means that the ID of the transaction that deleted this record. This record was not deleted by anyone yet, right? And these columns, just let's forget about them. It doesn't make sense right now to discuss. But right now, let's do this. Java Joe was executing the load test. He inserted some data, and then he updated some records. And here is, we will start looking into the garbage and how garbage gets generated at the database level. So what I do next, right? Let's say the pizza is in the queue, the status is ordered, but right now the chef is ready, and the chef is going to bake this pizza for us, which means that let's change the status. So we need to change, let's execute this put command, and their endpoint name is change status. That's the ID of the order, number one. And also we are changing the status to baking. Okay, all is good. Now let's do this. So the status has changed as expected, but let's look into the memory. Right now we have two records. The garbage, right? The garbage gets generated. So that was our first record, the first one. And you see that right now it has the Xmax ID set to 495. That's the ID of the transaction that deleted this record. So generally, this update, the second update that was changing the status from order to baking, it marked this row as deleted, and it inserted the new row. That's the idea of the transaction. So effectively, when you work with PostgreSQL, MySQL, and I think SQL Server, Microsoft SQL Server is not an exception, when you do an update at the database level, you are deleting the previous version of the record, and you're inserting a new one. Let's see what happens next. The order is baked, and the delivery guy is here to pick it up and bring it to my door. So which means that our system has to change the status to delivering. Okay, so far so good. And right now, if we look into the memory, you have three records, right? That's the latest value, and the previous two were changed. If we continue this practice, so like after the pizza is dropped, we have the last status, yummy in my tummy. Hopefully, the customer would enjoy this pizza. And if you go here, let's do this check first. The status got updated. This is what my application would see, but internally, Postgres has 4 versions. And this might remind us of what's happening with Java garbage collection, right? When we update something, create something, garbage gets generated, and then over the time, garbage collector, a friend of us, comes in and cleans the data and make some space available for data. In the relational world, in the world of the databases, if they generate garbage like that, they also have a garbage collector. In Postgres, it's called vacuum. It's like a vacuum cleaner. It's a special daemon that we can launch. Let's do this. Let me quickly.
For your screen, like what's the C stands for? When you insert the third record, there is 496 has no C there, but then when you insert the fourth 497, and then the all previous one has C. What does the C stands for in the Xminima and Xmax?
Yeah, this one, it's available. C. I actually don't remember. I don't remember what this means. I need to look into the Postgres source code. I don't remember. But I can explain you what this means. Generally, we have an index. And right now, the index looks into the heap only tuple. Yep, at this record, you have this index. So if you do the search, the index was not updated. So the index looks here when you do the search through the index, give me this record where ID is equal to 1. The index will come to this version, and this version says, take a look at this version, 0 number 2. It will go here, Postgres, and this one says, take a look at 3, and this one says, take a look at 4. So this is how it traverses. So eventually the index also can be updated, the B+3, but that's doesn't happen all the time. This one, man, yes, I don't remember. I need to take a look what it means.
I got a question as well. So this is just metadata. Where is the actual content? Does it actually have the content that represented those 4 entries?
Yeah, it's actually, so this is the metadata and the function. I can show you the source code for this function. So when you query, this is a special extension of Postgres that allows you just to look into the page. In the beginning, you have the header, and this is the information from the header of your page. And then inside of this page, you would have the payload, the data that you actually store. And this extension that is called page inspect, it basically allows you just to remove that payload and just to look into the state of the header.
So is the data in the write-ahead log somewhere?
No, the data is in the, So right now we are reading from memory. It's like in memory buffers of Postgres. Postgres also uses memory buffers. It caches data in memory. And this all is read from the memory. Also, if you try to look, it stores all the data to the write-ahead log file. Yes, it can crash, right? But it always can replay the data from the write-ahead log file. And then all of the time, also the data gets written to the files on the file system. Once Postgres writes this data to the files on the file system, it can shrink the size of the write-ahead log file. But this one, yes, by default, as long as the data, the pages are in memory, it reads it. If you're trying to get a record that is stored in the page that is not in memory, then Postgres goes to disk. But right now, that's a tiny database, 1 record. All this stuff is in memory.
Not to deviate from the topic, but the question is, this looks like kind of audit trail of changes, if I'm not mistaken. So is it possible to identify the nature of change and what the change was? Is it possible for you to do that?
So if you're talking about like auditing,
it seems like it's kind of audit trail of.
Audit is like, yeah, audit is this extension does not, and this function uses page inspect extension. But usually if you want to see what exactly happened, right? Let's say a value of the record, a value of the status was baking before, and then you changed it to delivering. This one, usually how you do with Postgres, you create a trigger. And for that trigger, when anything gets updated, you can write your change in another audit table. And then, or you can send it through a CDC pipeline. So this is what usually happens.
So you didn't automatically do that in your fetch, right? So these entries don't represent a state of data at some point, it's just a metadata.
No. Like those are the headers. Yeah, those are the headers of the actual entries. So like let's say that this is the page number 1, and this page of number 1 has like this page number 0, the first page in this table. And inside of this page, the size of the page is 32 kilobytes. And inside of this page, we already store 4 values, 4 complete copies of the records. But the only difference between those copies, the status column that was changed. So we don't show, let's say that like that's the first record, you have this header, you have some other metadata, and after that you have the actual data. It's just not shown here. That's just one single page, and the ID of this page is 0. You can change, let's say, from page number 0 to page number 1, but this page doesn't exist yet because I just have, let's say, 1 actual record and 3 copies of this record stored in the database. Okay? Makes sense? So let's quickly talk about our garbage collection. All right, this one we can skip. Vacuum. It's called vacuum. So how it works? This is our page. You've seen this page. Right now, our page has 4 versions of the records. And the page can look as follows. Let's say you have used data, some live data. When you insert more than 1 record, you might have order with ID 1, 2, 3, 4, and 5. And this is labeled as used. And also you can have dead records, those old values that are no longer visible or used by any running transaction in Postgres. And you certainly have some free space in your database. And vacuum, similarly to Java, in Java, garbage collection can run concurrently. And same as Postgres. Vacuum can run concurrently with your database workloads. So generally what happens all the time, the vacuum would start, there are different thresholds. It can be size by threshold or some timeout. And it will walk through all of the pages of different relations and your indexes. And it will label the dead sections of your page as free ones, as available for the future data. Okay? And as long as it runs concurrently, it doesn't block your application selects, updates, deletes, and inserts. But also there is the full vacuum operation, and it's similar to the stop the world pause in Java garbage collection. You remember, let's say, when Java garbage collector cannot keep up with your workload and your application is running out of memory space, garbage collector can stop your application workload and start aggressively collecting, compacting the heap. And Postgres can do the same, but usually this can happen manually when an administrator executes this command. But in the world when all of the applications has to function 24/7, many database vendors, especially those who create database as a service, they found a way how to just rely on the auto vacuum and prevent the full vacuum from happening. But the beauty of the full vacuum is that, yes, it will stop your application workload, but also it can compact your pages. For instance, in the previous example, you see that we have a sort of a defragmentation. So you have used, you have free used, and when you do the full vacuum, the live data is moved closer to the beginning of your pages. And this space, free space, if needed, it can be returned to your operating system so that other processes and applications can use this space on disk as an option. So let's run this command. Let's do the vacuum. Let's return to the application. So let's check. Yeah, we still have all those records. And if you run, we can enforce the auto vacuum, the one that doesn't block our application workloads. If I run this one, you see that what happened. So this page is referenced from the index. And when you are doing the search through the index, the search will come here. And it said that the actual data right now is stored in this place, at this offset. And this data is unused, meaning that it can be used freely by other records. Okay, this is the after vacuum. No any compaction, but some space is already available in the middle, let's say, of your page. So let's try to do this exercise. Let's see that when I'm updating my records or inserting new data, I want to make sure that Postgres actually can reuse this space. Let's go to my application, and I think I have, let's try to change the time. Order time, today is 2012. And it's 1937. And the name of this order status, order time. Okay, now. So it's named change order time. Okay, it's changed. It's exception, right? Bad request because of this. Yeah. Done. No exceptions. So right now, if you run the same one, you see that this one is used. So instead of adding and using the space down the page, Postgres reused this free offset, right? So this is actually what's happening with Postgres, and similar things happen with Java garbage collection, okay? Finally, let's try to do this. Let's try to update this or delete this order and see what happens. Because if I ask Postgres and my database to remove this data, is there any change? Let's do this. We need to remove this one. Have data. Delete order, I guess. Delete order. And delete. Deleted. So if you run the same operation, I mean it's deleted. You see, that was the last value, and it said that that's the ID of the transaction that deleted Xmax. So the record is no longer here. If you execute this query, the page is empty, but not the actual memory space and disk. And as an example to show you how vacuum full works, if you execute vacuum full, sort of full stop the vault garbage collection in Postgres, it will take longer time to execute because it also needs to rebuild the table and index. But once you run it, the memory is empty. It's like it's completely gone. Because right now we don't have any records and all the space is available, okay? So that's Postgres, and this is what happens at the database level.
So would this not delete all the state information? So let's say if I want to roll back to a previous version, would this not, would the vacuum not remove the possibility of moving back, rolling back?
The data is stored in the write-ahead log file, and then depending on your settings, you can decide for how long the data can be preserved, and then you have an ecosystem of different tools and extensions that can help you to pull the data from the write-ahead log file. You can send it to other databases, or you can take backups. But usually, yeah, it depends on how active your application. Probably, I mean, time-wise, Postgres might be running out of vacuum every few minutes, or like 10 or 15 minutes. And also there is a size-based threshold. But anyway, the write-ahead log file is a friend of you if you want to look back in the time, and snapshots are there. Okay, wonderful. So let's move on. So it turns out, and actually a quick conclusion about the after vacuum, it's not limited to the garbage collection. It's certainly, as part of the garbage collection, it helps you to recover and to reuse disk space that was previously occupied by previous versions of the records. And also, Postgres as a database. Whenever it executes your query, some of the queries are much more advanced than those that I was executing. You can join data, you can have a lot of filters in your where clause, etc. And Postgres needs to collect statistics. Just understand like what queries like I used the most, and should I use index or should I do a full scan over my data? And usually the statistics are also collected during the vacuum process. And there are some other Postgres related things. So as for the recommendation here, because from the learning perspective, this might be something new for some of you, because databases as Postgres, they do use garbage collection, and when even if you create a simple web application with Java, you will generate this garbage in Java, but also you will generate it underneath. It's not just Java, right, per se, but any application that will be running on top of Postgres will be generating that garbage. And as an advice here, always do the load test of your database. Just don't, when we test, let's say, create the first version of the application, we can use some embedded databases, but always try to run your application against your production database, and do this for a significant amount of time. Load data, update data, and delete data, and see if that will impact your performance. By default, as an advice of an engineer to an engineer, just don't touch the auto vacuum or vacuum settings by default unless you're sure. If you need to tune, if your load testing shows that something goes wrong at the database level, then just talk to an expert like a DBA. You might have a DBA on your team, or do it yourself if you're an expert in the databases, or if you're using a serverless database or database as a service, usually those guys who run that service, they will take care of everything that is related to the garbage collection at the database level. So now, let's quickly look at the other database, because that is built on PostgreSQL, but its storage engine is different from Postgres. So once this pizza shop was launched, it was opened, let's say, in one of the cities of Georgia, but then eventually it became a big hit. In Java, Joe decided that we need to launch it nationwide. And this is the time to test the next architecture when you want to have a distributed database. So quickly, one slide and two slides about YugaByteDB. It's built on PostgreSQL, so eventually you're going to use Postgres. It runs on Postgres. It's PostgreSQL source code, but the storage layer is not Postgres. Postgres uses B+3. It has its own memory structure and disk structure, but YugaByteDB is inspired by Spanner, Google Spanner. It's a distributed SQL database that is available on Google, and it comes with automatic sharding, distributed transactions, raft, and blah, 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 blah. So this one we can skip. So usually, as a hint for you, if you ever decide to use a distributed SQL database such as YugaByteDB, why would you use it? As long as that's a scalable database, if you want to withstand various cloud outages, you can run your database across multiple cloud zones and regions, and every database nodes are active readers and writers. It's not like Amazon Aurora, when you can read from any replica, but you can write only to one node. Also, you can serve requests with a low latency around the globe or around distant locations if you also deploy your database across several places. And you can expand across continents by complying with data regulatory requirements, because you can decide if this data belongs to the one who lives in the European Union, these records have to be located on the servers in the European Union. The other data, let's say, can be in the United States or somewhere in Asia. So, and YugaByteDB is a LSM-based tree database. So if you have anybody heard about LSM trees? Like Cassandra. Cassandra is a good example of a database that uses LSM trees. YugaByteDB also uses LSM trees, but YugaByteDB is a transactional database. So just a quick introduction to how LSM tree operates. Let's say you have a write. Your application wants to write a data. We put a new order, pizza order, in the database. This write First will be written to a mem table in memory, and also it will be recorded on disk in the write-ahead log file. Okay? Then over the time, this mem table will get populated because you insert new records, you update records, and over the time, the data needs to be flushed to disk to SS tables. And here we have multiple levels. In this, let's say, SS table, we can keep keys with the ID from 1 to 500. In this one, we can keep keys from 500 to 1000, etc. Let's say order ID from 1 to 500, from 500 to 1000. And the same is true, like all of these SST tables from different levels, they might store old data, garbage. Because similarly as with PostgreSQL, with LSM trees in YugaByteDB, you can have multiple versions of the same records for the same reason. When you have multiple transactions running, you want to be sure that transactions don't conflict with each other and you only see already committed data, right? But there is also the notion of the garbage collection. It's called compaction. All the time, a special process, thread, will be started. It's called compactor, and it will go and merge these SST tables. For instance, if for this order ID is 1, here is I might keep, let's say, the value of the record where the status was ordered, and here is right now I have the value of the record with the status delivering. They will be merged, and the value with the ordered status will be removed. It's no longer needed because no any other transaction uses this record any longer. And when you read, actually, there is a possibility for the read amplification with this structure. Because let's say you want to read an order with ID number 1. First, mem table will be checked. If the latest value is here, it will be returned to your current transaction. If it's not here, then this immutable mem table will be checked. And this immutable mem table is flashed to disk. If it's not in memory, then this order with ID 1 will be checked, let's say, here. If it's not here, then it will check the other tables that keep the ranges, let's say, from 1 to 500. But generally, like, this search is really quick because it's a logarithmic search. You check here, you check there, and that's fast. This one we can skip. So right now, let's do a similar test, but with YugaByteDB, because with YugaByteDB, we will find something else, something interesting. So with YugaByteDB, I want to, let me disconnect from Postgres. I want to go to the settings of my application. So let's tell the app to connect to YugaByte. Okay, looks like it connected, and right now I'm connecting. It's also runs on my local machine. Just single node, not a distributed cluster. It listens on a different port number, and the username is YugaByte. It's empty. It's not empty because the application started, and we have this table, but there's no data yet. So let's quickly do this. YugaByte, the disk storage I showed you, is different. So like this function doesn't work with YugaByteDB. There is no such extension that exists for Postgres, because that's a LSM tree. It works differently. But we are going to look into the database files of YugaByteDB to see how multiple versions gets generated. So right now we will do this really quick. Let's put this order with ID 1, and let's update the status a couple of times. Status, let's change it to baking. And then we can change it to yummy in my tummy. So right now, if I go to YugaByteDB, so that's the latest status. And if you want to check that the database, this database also generated and still keeps multiple versions of the records, we can do this by looking into the database files. Don't repeat this at home, because usually you don't need to do this. And I don't remember these commands by heart. So what I'm going to do, I have a cheat sheet. So here is, let me look for Yugabyte. I'm connecting to my Docker container that runs Yugabyte DB. And then I need to know the internal ID of this table. So there's the internal ID. And next, I want to flush, because by default, you remember mem tables. Right now, the data is stored in mem tables and in the write-ahead log file. There is no any SST file on disk yet, because usually the first SST file in Yugabyte DB will be created when you at least get 140 megabytes of data in memory. That's why I want to flush it. No, that's a different command. Yeah, that's the flush. We flushed it. So right now we have an SST file, and right now I will find it on my file system. So we need to use this table ID. And this is the first SST file. And for that one, yep, I want to show this output. All right, so let's decode this. So what we see here, it's a full mess, but I will do this, guys. Much better. So let's take a look. Column number 1. And this column, we change the status. You see this one? So the status was changed multiple times. So basically, this is the binary representation of this column. At Yugabyte DB, when in Postgres keeps a full copy of your row. So like even if you update a single column, Postgres will keep an entire row with all of the other columns. This is how it works. At Yugabyte DB, it supports column level locking. And also when you update one of the columns, such as the status, only the new value of this column will be stored for the sake of multi-version concurrency control. And this is what you see here, all right? Also, for some reason, we have order time column, multiple versions for the order time column. But you see that the value the same, right? This 7.2 number. It has not changed. Why this happening, right? For the God's sake, why when I was updating just the status column, why Yugabyte DB decided to keep a copy for the order time column? And here is the answer comes if you check the query that gets generated by default by Hibernate. When you update, by default, Hibernate will ask your database to update all of the entities. How to fix it? so we are not going to see it today, but a quick fix for you that you should remember is with databases that support column level locking and that can keep just versions of your columns, use this annotation, dynamic update. With this annotation, Hibernate and Spring Data JPA, they will be tracking changes of your entity class. And when you will be doing update, only the updated columns will be sent to your database, okay? So if you wanna quickly do the check, let's restart this application. And if we go to our endpoint, let's add a new order with ID number 2. And then when you do update, Hibernate no longer generates, it excluded, right, order time from the generated query. And this is ideal for the databases that support column level locking. So keep this as a hint. With Postgres, with MySQL, Oracle, and etc., actually from the concurrency standpoint, it doesn't matter whether you use dynamic update or not, because it's just still they keep a full copy of your record. With YugaByDB, it makes sense to use this annotation. Any questions before we move to the last section? Make sense? All right. Hope it's fruitful. And now, yep. So same as with Postgres. I mean, distributed databases, they require even more attention. Do good load testing, inserts, deletes, updates. Keep an eye on how the database behaves over the time. Run this test for a couple of hours and see if any processes that are happening in the database level, such as the compaction, impacting your application. Because sometimes you also might need to tune compaction or some of the knobs and settings of your distributed database as well, okay? Just do the load test. This is what's on us. And the final thing. So Joe discovered, all right, so right now he is fully equipped, he knows about garbage collection. With Postgres, with YugaByDB, he feels confident. And then he does a load test for multiple days. He runs this load test, probably multiple days sounds way too much, but let's say an extended test, 5 hours, 10 hours. And then suddenly he sees some performance drop. First, the throughput of the system was high, but then it started decelerating and it got to this level. So what's happening? As an engineer, he checked everything. All is good with the application, with the JVM. No any symptoms from the database level, all is fine. But the only one hint is that SSD is 80% full. And that's the only one thing that is different from his previous test. So how does this SSD size can impact the performance and throughput of the application? So again, he started looking into the SSDs, how they are implemented and work internally. And actually, SSDs, they don't override already used or deleted sections of your block. So SSD operates on the block level, and inside of the block, you have pages. And every page usually is 4 kilobytes of size. So when your application asks the database to update some record, insert new record, eventually the database will send the page, right? It's a block I/O. It will send the page to the SSD. And if that's a new page, this new page will be written to a free space of the SSD. And then what happens all the time, you keep writing the data, but if you want to update a block, you updated, let's say, some block at your database level in Postgres. And right now you want to write this change to the Postgres files on disk. And this one was updated. But SSD cannot override it. Instead, SSD will write this new version of the page into a free page in the block. And the previous one will be marked as stale. Sounds familiar, right? The old data The old pages are not deleted, they are rather marked as those that keep the stale data. And again, SSD is like you write data, you update data, you insert, etc., etc. And the garbage gets generated. So all the time you might have a block that has a little of useful payload with a lot of stale data, dead pages, and just, let's say, one free page left. So what can happen? And SSD also has a garbage collection. And with SSDs, it's also called garbage collector. Like in Postgres, it's called vacuum. In YugaByteDB, it's called compaction. In SSDs, it's called garbage collector. So what happens first? SSD controller needs to find a block with pages that is completely free. And then it will move all the live data from block number 1 to this block number 2. So eventually, once this operation happens, block number 2 will have all these pages here. Oh yeah, I forgot to update the color here, guys. Sorry. Anyway, it had to say used. It's used. And after that, SSD controller puts the right amount of voltage, and this whole block with all of the pages gets erased. And the question is, yeah.
So when you say SSD does it, what do you mean? Like, is it the operating system does it? Right?
It's like controller. It can happen at the hardware level. It's like, yeah, firmware.
Oh, it's a firmware.
Yeah. But the question is like, my first question when I discovered that, why SSD cannot just erase a page? And the thing is like related to the physics. When you write or read pages from SSD, it gets, let's say, a different amount of voltage than to erase a page. For instance, if you decide to erase like this page, then it will put different voltage, and this way it can corrupt nearby pages. It can corrupt data in the nearby pages. That's why it's always erased at the block level. So this is why, and actually SSD vendors, those who produce those devices for us, they actually, when you buy a 100 gigabyte SSD, this is what's visible to your application. But in fact, manufacturers that put aside extra space for the needs of the garbage collector. And this extra space is called like over-provisioning. So this space is not visible to you. Let's say here it's shown that we have 28 gigabyte extra available for SSD to operate normally with good performance. And also SSD, but like why the performance degraded when the SSD became 80% full, right, with that test? Because garbage collector of SSDs also uses this space. So like if your application doesn't use, let's say, this space, your space, SSD also will be using it. As long as your application starts using most of the space out of this 100 gigabyte, SSD is getting less and less space for the garbage collection. And you can see this throughput kind of declining because SSD has to do its job. Let's say making some pages available, removing data, and making new pages available for your applications, okay? So here is, I'm not going to do any tests because I don't know how to do that. I didn't look into that. But again, as an advice, this is like a true, I faced this several times during my career when I worked for the previous company. We worked with one of the largest bank and some other retail company. And they were using a different database. They would run, let's say, a test for multiple days, and then suddenly they would see that the performance goes down. And turns out, usually it was related to SSDs. And usually their goal was to, they just, bought an SSD with much larger capacity. Or they would, let's say, deploy a database across multiple nodes. So that's why, again, do an extended load test and keep an eye on the SSD, if that's your responsibility. Nowadays, usually we don't do this. We have infrastructure team, we have cloud stuff. But if it happens that you run this stuff in your private environment, private cloud environment, and somehow you kind of receive a ticket saying that, hey, like what's happening with your application? And you look at your application, all is good. You're talking to the database guys, asking them, hey guys, everything is fine with vacuum or like compactor? They say, okay, then probably you need to talk to the infrastructure guys and say like, what SSDs, what's happening with the SSDs? So it can happen. It happened to me a couple of times, and this story might be useful to you as well. So, happy end for Java Joe. The pizza chain is already opened in multiple locations. And he figured out that garbage collection as a technique doesn't belong to the world of Java only. But similarly to Java, there are other technologies, best-in-class technologies such as PostgreSQL or SSDs that manage to implement and to use garbage collection properly. This is why those techniques are used in the wild. If you want to learn more about scalable applications or databases, this is my usual advice. Designing data, like all of the books are published by O'Reilly. First one is designing data-intensive applications. It's basically how to build applications for public or private clouds when you need to run application across multiple zones or regions and when you use different streaming platforms. Wonderful book. This one is cloud related, and that one is for those who'd like to learn a little bit more about databases, database internals. It's written by a database guy, but for developers. So it's easy to consume and it's easy to understand the difference between all of those B trees, LSM trees, like multi-version concurrency control and blah, 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 blah. If you're interested in distributed SQL, like Yuga by DB, because if you want to run your SQL and applications across multiple nodes, you can take free courses at Yuga by DB University. And if you have any questions to me, please find me on Twitter.
Is it open source?
What? Yuga by DB? Yeah, it's open source. It's open source. It's Apache 2.0. Thank you. Any last questions?
Yeah, you mentioned there was a difference with Aurora DB at AWS. Was it that it can support writes on all replicas? Is that what you said? I missed that.
So the question is like, I was talking about Aurora and comparing it to Yuga by DB, because both Aurora and Yuga by DB, they are built on Postgres. And nowadays, actually, those are not the only two databases that are built on Postgres. You have AlloyDB by Google that was announced a few months ago. You have some other databases. So Aurora reuses most of the Postgres, but it has a writer node, the primary node that is deployed in one of the availability zones, and it accepts, and all of the writes, all of the inserts, updates go through that node, and those changes get replicated synchronously to replica nodes. And you can read from those replica nodes, but you cannot write to those replica nodes. So generally, you can store in Aurora as much data as it's available on your writer machine. It's like vertically, you can scale vertically only. Yuga by DB is a distributed database. Most of you know Cassandra and MongoDB, and those are examples of distributed databases. They take and shard data across multiple machines. For instance, let's say that I store 1,000 records in Yuga by DB. Half of these records can be stored on node number 1, and the other half will be stored on node number 2. When you want to update data for record 500 or read record 500, the request will go to the node that owns the primary copy of this record. And then, let's say, when you run your operations, usually you would request different records with different IDs, different conditions, and all of the nodes will be load balanced, because every node in Yuga by DB, same as in Cassandra, it's both the writer and the reader.
I have a question. So how does Yugabyte compare to Google's AlloyDB?
AlloyDB, basically, for me, it's Amazon Aurora on steroids. Because what Google did, similarly to, the architecture is similar. You have one primary writer, the node that accepts the writes, and then you have multiple replicas. But also, Google claimed that they have a much better support for analytical queries. This is what Amazon Aurora doesn't do. But architecturally, let's say from the writer and reader standpoint, you can scale really well reads with AlloyDB and Aurora, but you cannot scale horizontally writes with those databases. With Yuga by DB, you can do this because it's like a shared nothing architecture. Mm-hmm. Which one? For what? It's like they're available. If you want to, there are certainly some artificial benchmarks, you can check them. But my always advice is just go ahead and test for your data. But it's, usually what people it's actually a good question because sometimes what happens, let's say someone needs to upgrade from PostgreSQL to Yuga by DB because probably they want to withstand outages in the cloud, or they need to just to scale reads and writes, or they need to store much more data in the database. And many start comparing a single node Yuga by DB cluster to a Postgres instance. In this case, Postgres instance usually shows much better performance because Postgres is optimized for a single server workload. Because when you run, right now, presently, with the current version of Yuga by DB, it's supposed that you're going to run at least, let's say, a 3-node cluster. So if you run this node cluster, if you store a good number of data in that cluster, then you certainly would see performance differences. All right. Has anybody knew, like, is there anyone who knew all this stuff that we discussed today? Anyone? Was it useful? Yeah? All right. All right then. Thanks a lot for coming.